So in this video, we'll be calculating how long my 3.7 volt LiPo battery will last with a Raspberry Pi and a function generator attached to it. We'll also calculate how long it will take for the solar panel to charge the battery. And then in the next video, we'll be solving the problem I run into at the end of this video. So subscribe if you don't want to miss that. So here's the current setup that we have for the project. If you don't know already, this is for my final year project in which I'll be creating a renewable energy educational kit that will teach hobbyists and students how solar panels, charge controllers, batteries, and DC to DC converters work, all within a renewable energy setup. This will be on a circuitry level, so the final kit will contain perf boards with components and tutorials on how to construct those circuits, all of which will be made by me. Now, in order for us to calculate how long our battery will last, we need to actually know a bit about the battery. So it's a 3.7 volt, 650 milliamp LiPo battery. It has a watt hour rating of 2.4 watts, which is calculated by multiplying the voltage, 3.7 volts, by the capacity, 650 milliamp hours. So what that means is that this battery can deliver 2.4 watts of power per hour. All right, let's talk about the battery runtime. This is the amount of time our battery can run for. It's calculated by taking the battery capacity in milliamp hours and dividing it by the load current in milliamps. So we already mentioned the battery capacity is 650 milliamp hours. So we just need to find the load current, which is the current that the whole circuit is using, i.e. the current is coming out of the battery in order to power the Raspberry Pi and to power the function generator. What we're going to do is to calculate the current draw, then we're going to add just simply a multimeter between the battery and the solar charger. So here we can see the current going into the battery and it's minus 300 milliamps, meaning that 300 milliamps of current is leaving the battery. This is when both the function generator and the Raspberry Pi are running at the same time. The current draw with just the Raspberry Pi is around 180 milliamps and the function generator is around 120 milliamps. That totals together to be 300 milliamps. Therefore, the battery runtime would be 650 milliamp hours divided by the current, which is 300 milliamps, which equals 2.17 hours, which is 2 hours and 10 minutes. And that's actually very much in line with what I tested it for. So I ran the whole circuit and left it running for a couple of hours. And I found that after about an hour 45, it all kind of shut off. So I'm guessing that the battery wasn't fully charged at that point. All right, so we've calculated our battery runtime. The next thing we need to calculate is how long it will take for our battery to charge, which is the battery's charge time. This is the amount of time that it will take for the battery to charge to full. So for our 3.7 LiPo battery, full voltage being 4.2 volts. Now at the moment, we have only 5 milliamps coming from the solar panel into the charge controller and then into the battery. So think about that, 5 milliamps. This would take then a whopping 156 hours to charge our 650 milliamp hour battery, or in other terms, 6.5 days. Obviously, waiting a week for a panel to charge a battery is ridiculous, so we need to do something about it. And the keen eyes amongst you may have noticed that I'm using an LED ring light, which obviously isn't sunlight and it isn't producing enough current in the solar panel. So when I connect the solar panel to my window, even though it's a typical rainy day in Britain, I get 8 times more current than the LED. So where I got 5 milliamps for the LED, I actually get 40 milliamp hours just from sticking it onto the window on a rainy day in Britain. So now if we use those calculations, so for a 650 milliamp hour battery, but with a charge current of 40 milliamps, then we charge our battery fully in 19.5 hours, which is obviously a lot less than 156 hours. So you may be wondering, what if it's sunny? For me personally, this is such a rare case in Britain that we get sun. So it's not even worth it for me to consider the sun. However, if you do live somewhere where you get sun, then I'll mention this here now, that solar panels on a cloudy day produce about 10 to 25% of what they would on a sunny day. So if you said that on a cloudy day, we was getting 40 milliamp of current going into our charge controller, that would mean that then on a sunny day, you would be getting 350, 400 milliamps going into your battery. So what that would mean for us at 350 milliamps, then our 650 milliamp hour battery would charge in just 2.2 hours. So just there, you've balanced your load and your supply. But as I mentioned, I'm in England, so I'm going to have to go with the cloudy measurements, which makes this a lot harder for me. So I would need 19.5 hours of cloudy daylight in order to charge the battery, which is doable over 2 days since we get about 12 hours of sunlight on average each day in the UK. So with a 650 milliamp hour battery, we need 19.5 hours to charge it on a cloudy day at 40 milliamp hours. Once we fully charge it, it will run for 2 hours and 10 minutes at 300 milliamps. that's still very far off balancing it. Thinking you're talking about 19.5 hours to charge it, whilst only running the project or the circuit for 2 hours. So I want the charge time to be equal to the runtime. So currently the Raspberry Pi is using 100 milliamps of current, and the function generator plus the boost converter together as a pair are using 120 milliamps. So that totals to be 300 milliamps. I could add a switch, for example, so that only one of them is on at a time. So if I had a switch between the Raspberry Pi and the function generator, then you would have to switch one of them off in order to turn the other one on. And so that would then limit the max current from the battery to being at 180 milliamps, which obviously is going to increase our runtime. So based on that, you would increase our runtime from 2.17 hours up to 3.6 hours, which is 3 hours and 36 minutes, which is still far off our 19 hours and 30 minutes it would take to charge. But it's an improvement, right? So the only other solution now I can think of at this point is to add more solar panels. You may be wondering, how does that work? If you add the solar panels in series, then you're going to get a much higher voltage. So the solution is to stick them in parallel. Then since I only need 180 milliamps, then if I take 180 milliamps divided by 40 milliamps, which is the amount of current I'm getting from one solar panel, and then that would give me 4.5, which is the amount of solar panels that I would need in order to reach the 180 milliamps in order to power the Raspberry Pi. Obviously, you can't get 4.5 solar panels, so that would need to be 5 solar panels. So if I had 5 solar panels in parallel, then that would produce an output of 200 milliamps going into the battery, which would more than cover the 180 milliamps that is used on the Raspberry Pi. And like that, we should be able to fully balance our supply and our load. So we'll do that in the next video. I've actually ordered them online now, so hopefully they'll come promptly and I'll be able to do that video. And then the hope is that we can power our entire system continuously off of solar as long as we've got it on. Obviously, there's no reason to leave it on the entire time, but the hope is that at least if you wanted to, technically you could. Obviously, I could add a larger battery as well, but that's just going to increase our charge time. And although we would have more runtime initially, eventually you're gonna, if you're at a deficit, eventually the battery is gonna reduce slowly. So something to keep in mind there. Lastly, obviously, when I create my own solar charger, my own boost converter, my own sine wave generator, then these current figures are going to be all completely out of whack. But regardless, this is a good learning experience for me, and that's what I'm doing this for. So that's it for me. I'll see you guys in the next one.